Yo, hello. You reached my voicemail.
Man. I'm not in my normal setup right now, so Wi-Fi is a little buggy right now. If it keeps interrupting, I might either have to reschedule or the video I planned for today, I'm gonna have to post it on Discord. Cause I for this week I had a new idea I wanted to try. So I got videos that explains what I usually explain about figuring out the process of what we're doing and then building the pseudocode and then that's when we get into the actual code. But and I was just gonna see how that goes, how people like it. But yeah, some stuff happened now. So I'm not in my regular setup. So the Wi it might be the connection might be a little in and out. So but just let me know if you can hear me right now though. I hope y'all can hear me, man. Okay, you can. All right, that's a bit. Is it blurry? With the way it is right now, do you think I'm good to start? Or do you think it'll be better if I upload the videos in code to Discord? Okay, we can manage. I think we can start if the share screen is blurry enough. We can't see. Okay, boom. So we'll get started then. Appreciate you, Chisholm. Okay, so like I was saying earlier, so this week I want to try a new method because normally I go on and I talk about what about what we have planned for the week or for the session. And I believe that instead of just talking about it and trying to give my live visuals, it'll be easier if I have videos out that are drawing it out so you can actually see the thought process. So we're gonna try that out for this week and you let me know you let me know what you think about it, okay? So first I'm gonna share my screen. Let me see. Let me share my screen. I'm not gonna share the Lilo platform yet. Window, entire screen. Infinite loop. Can you let me check the stream too. Okay, looks like because I'm trying to check it on my phone to make sure everything is lined up. Okay, so the we know that this week we're talking about the file system project, right? And when it comes to the file systems, basically they're just graphs, right? So when you have a folder or you have a file and then you're starting with the root folder and you're going, because remember we talked about linked list, right? We talked about arrays, we talked about linked lists, we talked about hash maps, which combine arrays and linked lists. So when it comes to file systems are just linked lists. But remember with the linked list project, I talked about how you can think about a linked list kind of like a treasure map where on each node is the blue is a clue, and each node is the not necessarily clue, but it's the paper that we can't see your screen yet in case you're sharing. Okay, right now it should just be on the infinite loop. Are you not seeing anything? Or are you just seeing me? I'm not on the Lilo platform right now, but you should be able to see an infinite loop on my screen. I'm on YouTube Studio right now. Okay, bet that. So in the linked list project, I talked about how a linked list is like a treasure hunt, and then you get a card that has the clue and the address of the next clue, right? So basically, the way the file system works on your computer is the same thing, but instead of just pointing you to one clue, it's pointing you to multiple next clues. Because remember, all the things stored in memory are just memory locations. So in with the treasure hunt, there's one clue that comes after, one clue that comes after that, and one clue that comes after that. But in this one, you can be it can point, right? So for example, if you think about it like you the mail person comes over to your house because you want to deliver mail to somebody, but not just one person. You want to deliver mail to multiple people, right? The mail person comes in and he sees all the envelopes in your mailbox with the red, and he knows, okay, I'm at this node right here, and the node being the house. And the node is telling me to go to these different places to deliver the mail. And that's how you can think of linked list and file systems or graphs, right? So a linked list or a doubly linked list is like points one or two directions. But when it comes to graphs, it can point an infinite amount of directions. Just like if you want to send mail to one house, you can, two houses, three houses, four houses, five houses, all the houses, right? So that's the difference between a linked list and a graph, but they are both graphs, right? So all of this is graphs. So the same way you think about going through a linked list would be the same way you think about going through the file system, because again, they are both just graphs. And with that being said, I will get started on playing the first video.
Computers build deep, complex file paths without creating duplicates or losing their place. To track their exact location in nested data, they use a traversal algorithm. Say you command the system to add root/docs/python/notes.txt, but it currently only has a root folder. First, the algorithm breaks that full path string apart into a sequential checklist of target names. Then it introduces its core mechanism, a single tracking cursor that starts right at the root. Before stepping into the next folder on the list, the algorithm must ask, does this folder already exist? If it's missing, the pointer creates it. Then it immediately moves inside that new folder, setting a brand new starting point. With its position shifted, it runs the exact same repeating loop for the next layer down, checking for Python, spawning it, and stepping downward once more. Eventually, the pointer hits the final name on its checklist. Because it's the last step, it creates your actual file instead of a folder, and the sequence stops. And that deeply nested text file from your original command, this single systematic pointer built every missing layer of that structure, just to put your file exactly where it belongs. How does depth first search?
Okay, boom. Were y'all able to see that video I just played on adding? Okay, bet. So as you can see, when it comes to adding, the first thing, it's no different than when you have to add into a linked list, right? Because like I said, a linked list is a graph. So as we're dealing with graphs, all these the concepts from linked list is going to be the same thing. The only difference is instead of just passing on a node, we are passing on a file path, right? And the file path is where it's what's telling us to go, is telling us where to go next. So we'll start with the root, then we'll go to the next part of the path, and then we'll go to the next part of the path, right? It's like when you go to youtube.com/studios/whatever, right? That's the file path, right? The root is youtube.com, and then in the server, so the file path in the servers, the root is youtube.com. Then the next part is, okay, I go to videos, and then I'll check, oh, is there even a videos to go into? If there is a videos, then okay, boom, I'll go into it, right? And then I'll check, I'll see, okay, video, I'm at videos now, and then the next part of the file path, I'll check for it again. Okay, so the reason I say graph is because graphs, trees, linked lists, they're all the same thing, right? They're all the same thing. But when it comes to a tree, the different, so actually let me be more clear. I'm gonna actually good way to call that out so I can actually clarify what was going on. So graphs, trees, linked lists, they're all the same thing, right? They're all graphs, right? It's kind of like a square and a rectangle, right? Like a square is a rectangle, but a rectangle doesn't necessarily have to be a square, right? Because a square is used in a specific situation, right? But at the end of the day, a square is a rectangle, right? It's a quadrilateral with 90-degree angles. So when it comes to a graph and when it comes to a tree, yes, a tree is a graph. But the reason we call it a tree and not just a graph is because the way it all starts from the root, and then it has a certain number of paths, and then as you're building it, starting from the root and working your way down, it has that tree shape, like that Christmas tree shape, right? It starts here, then it has these two children, then it has the next two children and the next two children, and then the children under that, and boom, boom, boom. That's why it's called a tree, because the shape of it is a tree. Now, the reason a graph is called a graph is just because it doesn't necessarily have a shape, right? A graph could be pointed at any direction. And technically, yes, technically, a tree can be pointed at any direction, but the reason it's specifically put in that tree shape is because the files at the root, there's layers to it. Kind of how, let's call the root your great grandparents, right? And then the children of your great grandparents, or you will start with your great great grandparents, and their children are your great grandparents, and then their children are your parents, and then your parents' children is you and your siblings, right? So it forms that tree shape. That's why, so a tree is that specific, where the higher nodes, the nodes above, have those children, right? And it's linked like that. That's why it's called a family tree, because when you put it in that, it doesn't necessarily have to be, even a family tree, it doesn't have to necessarily be in that shape, right? But it helps you visualize the correlation of each node when you put it in a tree. That's why that's just when it comes to family hierarchies, that's why they put it in a tree, right? And that's why they call this a tree, because it shows you that familial hierarchy, right? But with a graph, it's not necessarily a family, right? So there's not that family hierarchy. That's the difference between a tree and a graph, right? They're both, a tree is a graph, but it's a specific type of graph, right? A tree has familial hierarchy. A regular graph doesn't have a familial hierarchy. So what's an example of a regular graph? An example of a regular graph would be kind of like Google Maps, right? Google Maps under the system, it works as a regular graph, not a tree. Why? Because the location from like me to the gas station, or me to the library, or me to anywhere else in this world, or anywhere else in this universe, or anywhere else, period, it's not a familial hierarchy. It's not like, oh, the gas station came first, so it's above, and then the child of the gas station is Dunkin' Donuts because the gas station was first and then Dunkin'. No, it's not by family, right? It's just there's a path to get from the gas station to Dunkin' Donuts, and that's the connecting path, right? But then maybe Dunkin' Donuts won't be connected to the library, but the gas station will be connected to the library. And why is that? Maybe because to get from Dunkin' Donuts to the library, you have to pass the gas station and then go to the library, because maybe at this certain spot there's like a lake or something, so you can't drive over the lake, right? So it would make sense to just connect that, because if Google is showing you driving directions, it's not going to tell you to drive over a lake, right? But you notice how with Google Maps, it's there. So those nodes, and under the hood, Google Maps is just made of all these little nodes. So each address is its own node, and it's stored in this system in a way where everything is connected in a certain way where the paths that are available in the real world are represented in the servers. So that's the difference between a tree and a graph. I was calling it a graph just because, yeah, I call just because I know it's a graph. But to be more specific, since we are dealing with trees specifically, I will start calling it a tree. So thanks for asking for that clarification. So when it comes to trees, right? Like I said, because there's that familial hierarchy, that root is the grandest of parent, right? That's where the tree starts, at that root. And then from that root, you have the children, and then the grandchildren, and the great grandchildren, and the great grandchildren, right? And if you think about it, when you go to your your um your file system on your computer, you you can start off on, let's say, you'll start off at the root where you just open File Explorer. I don't know if y'all have MacBooks, Windows, both, but I'm just gonna go with Windows because I think most people have Windows. But you first open up File Explorer, and that's your root right there. And then from File Explorer, you can go into your C drive. So it'll be root, and then it'll be the C drive as the grandchild, right? And then from your C drive, you can see your documents, you can see downloads, you can even add folders, right? And those folders inside the C drive will be the C drive's grandchildren. I mean, the C drive's children, which would be the root's grandchildren. And then in those folders, they would have their own children in those folders. And it could be files, it could be more folders, it could even be an empty folder, it could be whatever, either a folder or a file. It can't be like whatever, but it could be a folder or a type of file. It could be whatever file, but it can only be a file of whatever, a folder or a file. Those are the only two options. But when it comes to a folder has no size, right? It's just a folder. It's just a container to hold the files, right? So, because the folder can be empty, so it'll have a size of 0. I mean, technically, the file can technically have no data. Like it could be a Word document with no data, and then it would be like 0 kilobytes or something. But you get what I'm saying, right? And then the file itself always has a size. So a file is either going to have 0 kilobytes, or which, if it's a 0 kilobyte file, you don't really need it, but you can keep it if you want, right? And it could be 500 kilobytes. It could be whatever the file size is. But that's how it works. And what that video was showing is when you want to add to a certain folder, what do? Like I said, you start at the root, you open up your File Explorer, then you go to your C drive, boom, and then you go to your documents folder, boom. And then in that documents folder, you can either add a file in your documents folder, or you can add a folder in your documents folder where you're going to then store a file, right? Like if you download something, right? So you can go to your desktop because like a file, right? Under the stuff on your desktop, you can also have files on your desktop. You can have folders inside of folders, right? So, but if you think about the path that you have to take, it's you say, okay, I want to go to my desktop files, or I want to go to my document files. What's the path? I open File Explorer, which is the root. From the root, I open my C drive. From the C drive, I open my documents, right? So if we go on, and because we've already talked about it with linked list, and it's kind of the same stuff, I already have my code preset. And so I'm just mainly focused on answering y'all's questions and then just walking through all of this, right? Since I just talked about add, I'm just gonna go over the pseudocode and the code. Then I'm gonna go through this information right here. Actually, I could just say it right now. So, like I said, file node, each file node, it'll come with a name, whatever you have to have a name for the file so we can easily access it from memory. It's gonna have a size, either a size of 0, where we're just gonna default it to a folder, or it's gonna have a size of more than 0, which then we know it's a file, right? And then we have, is it a file or is it not a file? And then we have the children. So the children the children would just be anything inside that folder, right? Anything inside that folder is the children. Now, this parse path function right here, all that's doing is taking the actual path that we're searching, and then we're just splitting it up, right? For example, if we had, for example, if we have roots, docs, resume.pdf, we're just going to split it into root, docs, resume.pdf in a list, right? So that's all that function is doing. And mind you, when this root is right here, it's because it's based on our local server, right? But that's how the internet works as well. So when you have like youtube.com or even learnwithleo.com, right? This is a file path. Like when it tells you HTTPS, that's just letting you know, because everything. So this is the difference between this and using just root docs resume.pdf is this is in your local system, in your local storage, right? But when you're on a website, when you're on the internet, it's still storage because everything is stored in a computer, right? So it doesn't change. The only difference is how do we access from one files from one computer to another computer, and that's what being online means. That's what internet is. It's just accessing files from one computer to being able to remotely access files from one computer to another computer. That's all the internet is. So it's just computers on computers. So it doesn't necessarily, it doesn't, the function doesn't change, the idea doesn't change, right? It's just, the only thing that changes is the amount of computers being used. So because we're on the internet, this HTTPS, it just lets us know that we're on a secure server. And then Learn with Leo is the domain name, which in this case would be the root, right? So domain names, learnwithleo.com, youtube.com, google.com, those are the root. That's the starting point, right? And it lets you know, the domain name is letting you know which computer or which server am I trying to locate my files in, right? And then it could be hosted in like Azure, AWS, your own virtual machine, or something like that. But it's all computers, right? So this Learn with Leo, the domain learnwithleo.com would be the root. And then this is the next file that we check folder, right? So it's root curriculum. Curriculum is the folder because here it has children, right? Because a file cannot have children because where are you going to put it, right? The file's children technically would be contained within the file, but that's not really its children. That's just the value or the or the data that it has, right? Like with the treasure hunt example, the clue itself isn't the child of, I mean, it depends on how you want to see it. So, hey, we can just keep it how we keep it. When it comes to files, the inside the file itself, but you can only store when it comes to file paths, only folders can have children, right? So that's how we can automatically know curriculum is a folder, right? So even like when I go to youtube.com and you see youtube.com/video, I know, okay, video is the folder, right? And so all this is doing is split into paths. Now, the next one is render tree. And all that's just doing is drawing. When you call this, you're just going to draw out that file path just so it's easy to see. So that's all that these startups are doing. And now let's get to add. So what did we talk about, right? First, we call this function the parse path function to split the files when we want to add a file. Right, so we'll split it so we know, okay, these are the different paths that I have to check to make sure that these are the paths that I have to check, because if I add a path that's already there, then it's no reason for me to add it, right? So in order for me to be able to check that path, I have to split up that path, and then first I have to check, is it an invalid path? Because what if the path that was sent was just an empty string, right? If we have an empty string, if we're getting sent an empty string, we don't want to have to do anything with that, right? It's not valid. So in that case, we'll just return false instead of wasting memory, or it's just to make things more efficient, right? You don't want to use up RAM to search up strings when you know there's nothing to search up in the first place, right? So boom, now that we got those checks out the way, like we said, to add, you'll start at the root, And then for everything after the root, for example, let's use the learn with Leo again. So you'll start at the root. There we go. So you'll start at the root, which is learnwithleo.com. And then for anything that comes after it, which would be anything from here all the way to here, anything that comes after it, we'll check if that child already exists, right? So we'll start with, so let's say we want to add this file path to Learn with Leo. So we're going to start at Learn with Leo, and we're going to say, okay, now let's see, does curriculum already exist? If it does exist, then we can just move into the curriculum folder, right? And then once we move into the curriculum folder, we check if this exists. If it does not exist, then we'll add it. If it does exist, then there's no reason to add it. We can just return, right? But let's say now, again, we're adding. We say, okay, does curriculum exist? And we look and curriculum does not exist. Then that's when we have to add curriculum to the file, right? Or to the root or the folder, my bad. And then once we've done that, then we'll add it and then we'll move into that, right? And then we want to return true. Why? Because it lets us know that we were able to get through with no problems, right? It's a confirmation for us. Boom. And then the pseudocode, this is the actual code. So first we check if we'll parse the path. We check if we do our invalid path check. And then this is where we start checking. We'll loop through the path, and then we're checking if the child exists. We're creating a new node. We're attaching the new node, and then we're moving downward into the tree, right? Boom. Now we're gonna go on to listing everything. Let me, sorry.
Map file paths without getting lost in deeply nested folders. Take a simple computer directory. A main root folder containing a docs folder holds a resume file. Reading the top folder takes the same steps as a file 10 levels deep. At any moment, the algorithm only tracks two things: the current location and the text path that got it there. Starting at the top, it lands on the root directory and records its path as just root. But when its mums a little down into the docs folder, how does it build the new path without reading from the top again? It uses a recursive handoff. Before moving down, the parent takes its own path string, attaches a slash and the child's name, and hands that pre-built path directly down to the child. Now the docs folder operates as its own starting point, repeating the exact same function to hand the extended root/docs/resume path down until no items remain. And this identical repeating loop cascades downward, eventually mapping out every single file on your entire computer. How do you measure?
Boom. So, all right. So let's talk about what just happened with that, right? So when it comes to figuring out all the paths that are available and all that are there, it all starts off with the root. Because when you start off at the root, all you know is I'm at the root and I have the location of the root, right? I have the file path of the root. Now from the root, you see, okay, the root has, let's say it has a documents child and it has a photos child, right? So that means from the root, what do I know? There's at least a root slash document, and I know there's a root slash photos, right? So what am I gonna do? I'm a I'm a save I'm a save root slash document and then send that path over to the documents folder as the starting path. Just like with the root, the starting path is root because you have to start somewhere, right? So now the documents folder, when you go into it, it's starting off, its root is root slash documents. Then from the photos, it becomes root slash photos, and you pass that on to photos, right? And that becomes its root file name. And then that traversal order keeps going on from one level to the next level to the next level to the next level. And then by the time you get to the bottom level, to the last children, which would be like leaf nodes, right? And a leaf node is just a node that doesn't have any children, right? So when you get to the leaf node and there are no children, then you know you have the full path, right? Because you've been inheriting the path from your parents, which inherited the path from their parents, which inherited the path from their parents. When and now all it takes is just the last child just adding its path or its name to the end of the family tree, right? So all we're doing is we're creating an empty list, and this is where we're gonna store the file path, right? And this traversal idea that we're talking about is called depth first search, where you're searching. There's two types of searches, right? There's depth first search and there's breadth first search. Depth first search means you're going all the way as deep as possible, and then you're making your way up. You come back deep, make your way up, come back deep. So you're going from into a folder, into the next folder, into the next folder, into the next folder, all the way till you get to the end where you can't keep going anymore, right? And then boom, you're going as deep into that folder as possible. Then there's breadth first search. And breadth first search means you check the whole folder first, and then you go deeper into the next folder. And then you check the whole of that first. So you're starting at one level, and then you're checking that whole level first. Then you go to the now into the next level, and you check that whole level. And then you go down to the next level, and you check that whole level. Both ways allows you to both ways allows you to check everything, because you will be checking everything in that um you will be checking everything using depth first search and breadth first search. So they can be interchangeable. It just depends. It goes from situation to situation, right? Whichever just makes sense in the moment. But at the end of the day, you are getting the same information because they both check every level. So, but here we're using depth first search, where we're taking the node and then we're passing in the node and then we're passing in the path, right? So we're gonna save the current path, and then for every child, we're gonna visit that child, and we're gonna store the results of that. So we're visiting the child, and then that remember we're adding to the path that we're passing on to the next child, right? And then at the end, we're gonna sort the results so we can have it in order from level to level to level, right? So one is going to say root, then it's going to be root slash documents, then the next one, root slash photos, and then it will be root slash documents slash um word that doc, right? Or um bank statements that PDF, right? And then it would be root slash photos slash vacation that PNG, right? So that's all that is going on when it comes to there. And then we're going to return that sorted result, right? Boom. And now we're going to max depth. And max depth, it also uses a depth first search because it's in the name that's looking for, right? It's the max depth. So instead of just storing the path name, you're you're keeping track of the depth, right? So the same idea of storing that path name where okay, again, you start at the root, just like before. When you start at the root and you're trying to figure out the file name, the path names, you say, okay, well, when I start at the root, I know I at least have root. And I check, does root have children? If it does, then I know for sure I have root, and I have root slash documents and root slash photos, right? I know that for sure. When it comes to max depth, what do I know when I start at the root? I know the depth is at least 1, right? Because the root is a depth of 1, right? So I'm like, okay, boom. Then I check, does the root have children? It's like, okay, boom. If the root has children, then when I pass it on to the children, I know I'm passing on, the children counts as 1, I count as 1. So when I pass my 1 on to the children, to my child, it becomes, now my child has 2 because it inherits my 1. The same way it's inheriting my file path as the root, right? So it becomes root slash child slash grandchild slash great grandchild. And so the idea is the same. And you're just keeping track of, instead of keeping track of the file path, you're keeping track of the longest depth that you've seen, right? Or the deepest depth that you've seen, however you want to phrase it. So it's literally the same idea as list all. Max depth, list all is the same idea, right? Boom. When you want to get total size, again, all of these things, like when it comes to traversing, like I said, there's 2 ways to traverse um a graph or a tree. It's either depth first search or breadth first search. And one thing you'll notice when it comes to tools, that's why like when you start doing these over and over again, you realize you're just doing the same thing over and over and over again. Like when it comes to depth first search, it's just depth first search, and you're just keeping track of whatever it is you're keeping track of, whether that be the file path, whether that be um the depth, whether that be the total size, right? So with total size, the same way we just went over max depth and we went 1 by 1 by 1. Now instead of just adding 1, we're and passing that on, we're keeping track of the total size of the current node that we're in, right? So here on max depth, on list all, what we were passing on is the file path. Max depth, what we were passing on is the depth level, right? The depth level. And now what we're passing on is the weight of the file or the size of the file. So if it's a folder, the folder doesn't have a size. So it will be 0. With the file will have a size, and then you can pass that on, right? So you're just doing the same thing over and over and over again, right? Okay, boom, find. Let's say you're looking for going through, you're just going through the whole, you're just starting from the root. So you have the full path that you're starting from, and you break that path down into the different bits. So that's root, documents, bank statements. So I'm like, okay, boom. I'll first start off at root. I look, if I do not see a documents folder, then I just show, okay, there's nothing to return, right? So I return none. But if there is a documents folder, then I go into that documents folder and I check, is there a bank statements.pdf? If there is not, I return Then I return the documents.pdf, which would be current, right? When it comes to delete, so with delete, one thing about the root node, right? So if all you have is the root, then you'll just return false. So with delete, you have to return true if the deletion went through, if the deletion was successful. You return false if there's some reason you couldn't delete the path you were trying to delete, right? So if it's an invalid path, return false because it's invalid. If it's a root node, then return false because you cannot it that's also invalid. Um you cannot return, I mean, you cannot delete the root, right? And if you're checking, yeah, so and then if you see a file is missing or a folder is missing from part of that path, then you cannot delete it because it's not even there to delete, right? Boom. So these kind of fall in the same category. And once you get to that first spot, that first folder, like if you want to delete everything in your documents folder, and let's say your documents folder has a PDF, it has a bank statements PDF, it has quarterly statements PDF, it has semi-annual statements PDF. You don't have to go delete all those PDFs one by one, right? All you would just have to do is delete the folder, the documents folder itself. And then once you delete it by disconnecting that path. Because again, all of these things in memory are just parts of memory pointing to other parts of memory. So when you stop that pointing, then it automatically, so it gets deleted. That's how it happens. That's what happens under the hood. So it gets automatically deleted. Why? Because there's nothing pointing to it anymore. So what's the computer going to do? The computer is going to end up noticing that and being like, okay, we're going to use this storage for something else. Like, it doesn't actually delete in the moment, it just gets overwritten, right? So the computer knows, okay, now the stuff in this memory address, I can override the information in this memory address since it's deleted, or it's deleted. So I can use that to maybe store I don't know, a new download, right? Or a music download or something else, or maybe to even help your computer run faster, right? That's why sometimes when you delete, your phone can lag when you don't have enough storage. Then you delete stuff. Now the computer can use that extra storage, extra space, extra memory to help your phone run faster again, right? And it's not lagging anymore. So that's all you're doing. You're going to that first folder, that first parent folder that's not root, and then you're just deleting all that, unless there's a specific document that you're trying to delete, right? If it's just one document. But if you want to delete everything, that's how deletion works, right? So actually, let me show all this at one time since I was talking through it. Let me see if it's a question. Order, bottom to top, that's post order. Thought max dev can be done. Yup. Boom. On to searching by name, and I believe this is the last one. So again, when you're searching by name, you start off with the root. You go on to the next part of the path, and you look. Okay, is the next name here? Boom. Is the next name here? Boom. All the way until you get to the end, and you see either it's missing or it's there, right? And what is that? You're just traversing the tree. And what did we talk about traversing? There's two ways to traverse, either depth first traversal or breadth first traversal, right? And in this case, it's more so on the death first search side. And the reason it is because you wouldn't necessarily want to breadth first search. Well, I guess from level to level, you are breadth first searching anyways. You're just not storing it. You're just ignoring the parts that aren't what you're looking for, right? Because it's a breadth first search to look for the file that you're looking for. For example, like, let me use that our Lilo example again. So if I know this is the root and I'm searching in the root for curriculum, I have to breadth first search the Learn with Leo root to find curriculum. But if I'm looking and I see, okay, this is not curriculum folder, don't do anything with it. Just move on. I look at the next one. This isn't curriculum folder. I don't do anything with it. Move on. I look at this one. Oh, this is curriculum folder. Now I use that information how I need to, right? And I know I can go into it. So it is technically breadth first search that we're using. But in this situation, it's visually depth first search, but technically it's visually breadth. So I really could have called it breadth first search to be as specific as possible. But in this case, it really wouldn't matter if you called it breadth first search or depth first search, because it's kind of both. This is a situation where it's kind of both, even though it's also, it both works. And this is like a situation where both works. If you want to call it depth first search, you can do that. If you want to call it breadth first search, you can do that. Technically, the computer is breadth first searching though, technically. But as it's walked through, it's like visually depth first search, but under the hood, the computer is breadth first searching by like default, right? But yeah, so you're literally just going from, you'll break the path up into bits, into the different parts or components, and you check Learn with Leo root, you check for curriculum, and then you check for this, right? And either you found it or you didn't find it, right? And yeah, so, and if we submit, oh, I might. All right, submit anyway. Boom. I hope everything was able to be seen with the videos and the talking. And the reason I show all the videos, a lot of this, when it is a lot of graph/tree traversals, is breadth first search and depth first search. And you're doing the same thing over and over again. So it's like the videos for every section, or like going in depth into every section. Y'all don't necessarily need that, because like I said, you're doing the thing every time when it comes to breadth first search, when it comes to depth first search. You're doing the same thing. You're going to realize that when it comes to working with trees, right? You're going to be doing the same thing. So when you see a tree, when you see a graph problem, just know, boom, I can either breadth first search it, depth first search it, the information that you're storing and passing on to the next node, right? So if you're figuring out the file path and you're trying to build the file path, then that's what you're passing on to the next node. If you're trying to keep track of the depth levels, that's what you pass on to the next node. If you're trying to keep track of the file sizes, that's what you pass on to the next node. But essentially, the code, the logic is the same thing over and over. Like it's actually so repetitive when it comes to BFS and DFS. So I hope y'all enjoyed the stream for this week. Sorry for all the Wi-Fi issues. Like I said in the beginning, I'm not in my current office setup. So yeah, and then we had the storm earlier too. So it was yeah. So hopefully it wasn't too bad and y'all were able to see everything and I wasn't like cutting off too much. I didn't see too much about me being cut off or y'all not being able to see. So hopefully it went well. Hopefully y'all enjoyed. Let me get the Discord link just so I can have it. If y'all are not on Discord, this is the link to the Discord. Should have had that from the jump, honestly. You're welcome, and thanks for joining me on this walkthrough. I will see y'all next week. Oh, Wednesday, live mock interview. So live mock interview next Wednesday at 8. I will be back in my I'll be at a different setup. I won't even be in my office until like after this week. It's a lot going on this week. So this next week, I still won't be in my office setup, but I will be on the live mock interview at 8 p.m. on Wednesday. So stay tuned for that. Join the Discord. We already have it up there on the events. Then Friday, got another walkthrough that I'll be doing next week, Friday at 8. And then after that, I will be back at my regular setup, right? So join the Discord. Any questions that y'all have for me, y'all can always hit me up on Discord or you can hit up the team on Discord. Anybody, we're there whenever y'all need us. So I'll see y'all on Discord.